Hi, and welcome to the lecture ME210 on event-driven programming. This is designed to be a whirlwind introduction to how we apply programming concepts to the world of mechatronics. This is not quite as nuts and bolts as the basic circuits lecture is with regards to electronics, but we'll get into the nuts and bolts of programming in a later lecture. So, event-driven programming, what does it mean? It's a framework to apply to organize your thoughts. It's different from traditional structure of programming in that the traditional program structure is linear. It starts, it does some stuff, and then it ends. Think about like a mortgage calculation program where you have a set of defined inputs. You have the term, you have the interest rate, you have the loan amount, and some defined outputs. So it goes from input to output. And once the output is reached, it ends. The decisions made at runtime don't really change how the fundamental program structure runs. The mortgage calculator isn't going to change how it runs the calculation based on what the inputs and outputs are. But just changing the input changes the output, and that's about it. You take input from keyboard or data file, interactive or non-interactive, and you output to something, a monitor or another data file. However, you don't want your smartphone to have to end and reboot every time you finish making a call. So we need a different type of way of thinking about how you write programs for things like running smartphones. So when we think about programming mechatronic devices, the real key here is the program structure is asynchronous. Some stuff happens, some stuff doesn't happen. And when stuff happens, we want to respond to it. And when nothing is happening, we don't really want to do much of anything. There will be unpredictable sequences of events. So we can't rely on this thing happening first and then the next thing happening and so on and so forth. We have sometimes simultaneous inputs, as in things that appear to be in human scale at the same time, although for a computer, nothing really ever happens quite at the same time. We have to figure out how to deal with that. And there's no real end to it. The program will run until it runs out of battery or power or the Earth dies. For inputs, we have interactive inputs. We have sort of semi-interactive inputs, which are sensors, switches, other types of sensors, voltage sensing, and timers, which are sort of a special type of input that monitors time. For outputs, we could update a display just like a sort of traditional computer. We have the ability to switch stuff on and off, LEDs, heaters. We have the abilities to move stuff, motors, actuators, things like that. If we look at this set of requirements, this feels a bit like an operating system, like an OS on a computer. So we can think of programming each mechatronic device that we come into contact with as writing an operating system for a mechatronic machine that you've just built. So we introduce a concept called state machines. This is a tool for describing behavior of an event-driven programming task or event-driven program. It naturally fits with event-driven programming, and what event-driven programming is, we'll get down in the details later. And it allows you to explore the behavior of a program before you implement anything. That means that what we're doing is we're doing design. Design first. This is a tool that gives you the ability to structurally evaluate what your program will do before you actually sit down and write a single line of code. And it is quite possibly the most powerful tool you'll learn in ME210. State machines are something that people tend to write back to us about, saying, oh yeah, I used a state machine to break down this problem and it was really easy. So pay attention now for this lecture, or watch it at half speed if you're watching it online. Make sure you get all that we have to offer in it. Few definitions for a state machine. The full definition of a state machine is a finite state machine or FSM for short. Also sometimes called finite state automata, or FSA. It has a few very important constraints. At any given time, you can only be in one of a fixed finite number of discrete states. So you could have a state that's called running, you could have a state that's called walking, you could have a state that's called jumping. At any given time, your state machine can only occupy one of those states. The next state in the progression depends on the current state and the event that occurs. This means no history. It doesn't matter the order of states you jump through prior to get to the state where you are now. All that matters is that you're now in that current state. If you want to get around this restriction, you can store information, you can store historical information as discrete states. And you'll see how that works in one of our later examples in this lecture. Transitions, finally, from one state to the next are idealized and instantaneous. This turns out to be a pretty okay approximation of how actual implementations of state machines are in code. So we accept this, but when you have a particularly slow device or an old device or something that has a very long time constant, this may start to be violated, this assumption. So we have, to describe state machines, a thing called a state diagram. This is also called, with the unfortunate acronym of STD, state transition diagram. And what we need to represent are states and transitions. So let's say we have a state here. I'm going to call this state A, and we'll give it a name. Let's give it the name waiting. So this is the state I am in when I am waiting for something to happen. We represent states by circling them in. You could also box them, I suppose, but circles are easier to draw. And then transitions are represented by arrows. Transitions always happen between states, so I have to come up with a new state down here, so I'll call this state B, and we'll call it running. What I have right now is a state transition diagram with two states and one transition. And in addition to the transition, which has a specific direction, it cannot be bidirectional, so each transition has a direction. The transition has it associated with it an event. We'll call this event alpha, and occasionally also an associated action. This means that if event alpha occurs, and I am in state A, I transition from state A down to state B, meanwhile completing action alpha. There could be likewise a transition back from state B to state A that has some event beta, that's a B, no, okay, has some event beta and some action beta associated with it. What if we have a third state? So from running, maybe we don't go to waiting, maybe we have another state C here, which is an emergency stop. You could see why maybe sometimes we'd want to treat the emergency stop state differently from the waiting state. We might want to stay there for a while and make sure that whatever caused the emergency stop actually is resolved before we go back to running. So from running, we could have a transition over to emergency stop. We'll call this event gamma and action gamma. We could have a state from, a transition from state C back to state A with an event delta. Remember that while I'm drawing these are not required, these actions. Sometimes you can have transitions with no actions at all. So if I took this away, this just means that there's some event here, some event delta, that takes us, from state C back to state A, but otherwise doesn't do anything. It just changes states. The state is the internal representation in the program. Another thing that transitions can do is they can actually transition from a state back to itself. So if I'm running and some kind of event, let's say epsilon occurs, then I can perform some action, epsilon, and it doesn't transition states, it just does something. So you can think of maybe like a remote control, right? If you have a remote control with a bunch of buttons, a remote control is not stateful. It looks like, if you drew the state transition diagram for remote control, it looks like one state with a bunch of self-referential transitions back to it, because each time you press a button, it does some action but it never changes state. The buttons always do the same thing. If you really want to rack your brain, you can also nest state machines within states. So you can imagine one state which has a bunch of sub-state representations, and each of these works with transitions and actions to achieve some desired behavior, and then some transition might take you out of that state. Note that state diagrams are different from flowcharts in that flowcharts don't use events to moderate transitions. In a flowchart, you're always assumed to be transitioning through the state or through the box down through whichever arrow represents the decision that you're currently making with no thought that you're going to stay at a box for a certain amount of time or until something particular happens. Alternative formats for this are more formalized. They're known as UML state diagrams, but we won't cover them. State diagrams or machines. Okay. What is an event? The formal definition of an event is a change in an input. It's not input equals something. What we're interested in is when things change, that's when all the interesting things happen. If you can think of a signal that maybe goes from low or maybe dim to high or maybe bright, and this is with time here, if you can think of a signal that jumps up like this, then the fact that this input is high here is not an event. This is boring. Likewise, the fact that the input is low over here is also not an event. But this transition here, this is an event. This is the interesting stuff. And when we want to actually have behavior occur. So let's do an example for a smart combination lock, kind of like the one that's on the lab door. This is modeled after that type of lock. And I'll list some behaviors that we want. Usually when you're designing a program to drive a mechatronic device or a robot for the first time, you have a set of behaviors that you want, but you're not sure how to actually write a program that represents those behaviors. So this is a perfect occasion to use the state transition diagram to do so. So, like any lock, the first behavior we want is that the correct combination lets you in. The second behavior we want is that it's a little bit unusual, is if you key a wrong digit, it should reset the lock, as if you had keyed nothing. The third behavior, and actually I'll add to the first behavior here, and that this is an unlock. Unlocks the lock, lets you in, unlocks the lock. The third behavior that we want is pressing any key while unlocked locks. And just to make things interesting, the lock should beep on any incorrect digit. Okay, so if you want to take a minute to think through this yourself, you can pause the lecture now. Okay, let's give this state diagram a try. If I butcher this drawing, check your book on page 66, figure 5.4. Let's start with the unlocked state, or the open state. If the lock is open, based on our list of behaviors here, number 4 doesn't come into play, number 3 certainly does, number 2 doesn't, and number 1 doesn't. So let's make a transition that represents behavior number 3, which is pressing any digit. And the action is lock. So once we've gone from the open or unlocked state, and we've gone through this transition of, based on the event of any digit being pressed, and the action is locking the lock, we can call this new state something like no digits entered. I should mention that part of the requirements here that we want are a combo of 3 digits long, let's say. So we'll make a note of that here. All right, so from the no digits entered state, we want a transition that represents the first correct digit. The first correct digit in our sample combo is 2, so 2 pressed gets us on this transition to this new state here. Is there any action associated with 2 being pressed? According to our list of behaviors, we're not unlocked, so 3 doesn't take precedent here. 1 correct combo lets you in, but that's just the correct combo, so the first digit that you press, if it's correct, doesn't do anything. If it were incorrect, it beeps. So let's make sure we actually reflect that action too. We know that if 2 is pressed, you get to the new state here, but we also know that any other button besides 2 results in a beep. We also know that the incorrect digit should reset us back to the initial state, and because we're already in the initial state, that is a self-referential transition. So what should we call this state over here on the right? Let's call it 1 digit correct, because we've entered, at this point, 1 correct digit. So which are the possibilities, which are the states that we can reach from 1 correct digit? We can reach the no digits entered state by entering the next digit incorrectly, or we could reach the new state by entering a correct digit. So let's do this new state representation first because it's easier. If you press the number 1, now you've reached a state where you have 2 correct digits. If you press anything but 1, you'll get a beep. And because our behavior number 2 specifies we have to reset also as if you had keyed nothing, we have to transition back to no digits entered. The transitions out of the 2 digits correct state look much the same. We could either end up back where we started, or we can end up unlocking the lock. The last digit is in our sample combo is 0. And any other digit results in a beep and a transition back to this initial state. Have we covered everything? There's a slight subtlety here, and ignore that. If we look up here, we need an action to specify that the lock actually gets unlocked. Yes, we're transitioning from this here 2 digits correct state up to the open and unlocked state, but that doesn't mean that the lock is unlocked. There's no action associated with it yet. So the last bit of this chart is to insert an unlock action associated with transitioning into the unlocked state. Remember, the unlocked state only refers to the name of the state, which is an internal representation of the system, and it does not refer to what has happened. It can refer to what has happened. More frequently, it involves a gerund of some kind, running, walking, jumping, idling. But in this case, we need to explicitly set these actions. In this and every case, you need to explicitly set the actions so that they actually can occur and you can know better how to integrate them into your program later on. Okay, let's try a second example. And this one I'd really like you to try to do on your own after you pause the video, after describe what the actual prompt is, because it's actually a really fun one. So a garage door opener. If you don't have any idea of what a garage door opener is, then I suggest you go into YouTube and sort of find a video that actually shows you how it operates. It's also similar to a convertible top on a car. So the behavior that we want are that if you press the button to open the door, if you press the button, it opens the door if it's initially closed. If you press the button, it closes the door if it's initially open. It stops when the button is pressed while moving. It reverses direction and opens or closes when the button is pressed again after interrupted move. So if interrupted move means stops while moving, that's an interrupted move. It can sense obstructions at the floor and stop. So this is the default closing or closed position. So it knows when it's at the closed position. Likewise, it also knows when it's at the open position. I should probably put that on the slide for next year. It senses when resistance if it's closing and reverses direction. So unlike if you press the button while it's moving, if it senses resistance while it's moving, then it reverses direction. Also, this is only the case if it senses resistance while closing. Right? If it's opening and it senses resistance, then something's broken, but the garage doors don't actually reverse in that case. The light is to be on for 2 minutes after the most recent event. So we have one button, we have a door, and the door can go open or it can close. We have a light. And we have, a few sensors that help the door determine which state it's in, where it is, and what in the environment it's actually interacting with. So please pause the video now and give this a try. Give it about 8 or 10 minutes, and come back and see what solution you had and compare it to my own. Okay, how many states did you end up needing? 4, 3, maybe even 2? How many people needed 5 or more? So this is just my solution. What you'll find with state diagrams is that there are infinite numbers of ways to skin this cat. And this is still simplified with respect to an actual opener, but my state diagram takes 4 states because I do this with 2 stopped states. This is how I store the information about what the previous direction of the door was when it was moving. So I have these 2 stopped states here. We have to know whether the door was stopped while it's closing. We also have to know if the door was stopped while opening. The reason for this is we only have one input, which is the button, if the door is stopped. If the button can result in either opening or closing of the door, then we have to represent that as two different states, because the combination of which state you're in and the button being hit tells you what action you need to take. If we are stopped while closing and we hit the button, we get to some new state here. If we were previously closing and we hit the button, then we're now opening. Right? If you hit the button, if you're stopped while you're closing and you hit the button again, it's not going to continue closing. Because the opening and closing words here only describe the internal representation or the state in question, we have to add an action to this button event. So the action is door open, which would start to retract the door up to the ceiling. Likewise, if we're stopped while opening, if we stop while opening and we hit the button, we reach a new state here where the door is closing. And the associated action with that is door close. Okay, so for these two outer states, let's look at opening first. What states can we reach from opening? Well, if it's opening and something happens, we can definitely reach stopped while opening. One of those things is the button. If the garage door is opening and we hit the button, then it stops, and that we reach the stop while opening state. The action associated with that is stop door. What is another thing that happens? What is another event that happens that can take us from the opening state to the stopped while opening state? If you thought ceiling, that's right. So either the button or the ceiling can cause this state transition. Could it be that the door is not in the same physical position for these two types of events? Yes, but the door doesn't actually care. It just cares that it's stopped now. And that the next move, when you hit the button, would be to close. Likewise, closing, for closing to reach the stop while closing state, the transition could be caused by a button event, which would have an associated, action of stop door. Then, like the ceiling, we also have the ability to detect the floor. All right, what are we missing? We've got these guys here. We've got the stop when you button press. We need to reverse direction, and opens or closes when button pressed, again, after interrupted move. Sorry, that's not the one I'm looking for. I want the resistance one. This one, sorry. We do actually have this. This is good. Resistance when closing and reverses direction. So when closing, so we're over here, it senses resistance and reverses direction. Reversing direction would mean this direct transition. Does that make sense? The event is resistance. And the action is reversing direction or door open. Do we have an arrow going the other way? Not by the definition of the previous slide. All right, what are we still missing here? We've got this, we've got that. Light on for 2 minutes after the most recent event. Okay. Well, we need to, first, for every event, have an associated light. So in addition to all of the actions that are associated with all these events that we currently have, we also need to add the action of light on. Since the requirement for the behavior is that the light is only on for 2 minutes after the most recent event, we also actually have to have the capability to turn the light off after 2 minutes. Where does that end up in the state diagram? Well, the most recent event will be when you transition into a new state, right? So if we're in a state, and we're in a state for long enough that there isn't a new event to transition us to a different state, then we should expire the light, we should turn it off. So for instance, if I am in closing for 2 minutes, then after 2 minutes, which is an event of itself, we turn the light off. Oops. And similarly, because this could happen in any of our 4 states, each of them gets their own 2-minute light off self-referential transition. So if you have one that you think that can do it with fewer than 4 states, then good job. If you used more than 5, think about what you could eliminate to make it simpler to interpret. Like I said, there are very few wrong answers. There's definitely no one right answer. And so depending on how you actually structure the state diagram, your program is going to look very different from somebody else's program, which is structured around a different state diagram. Okay. We're going to shift from drawing some pretty pictures to implementation. Events and Services Framework is a conceptual framework. It's a method for implementing event-driven programming of state machines and emphasizes design first. It's an easy way to jump from state diagrams and state machines to how do I actually get to the point where I'm writing code. It decomposes the problem in a way that makes it easier to write code to solve it. This is sometimes referred to as the E&S framework. What are events and services? Well, events are just like in state diagram. It's did something happen? And by something happen, we mean something interesting. Did something change its state? And then a service is something you do in response to an event. Write these two things separately, the event checking code and the service code, and they're really easy to debug in isolation. So here are rules for implementing events and services. Rule number 1 is that there are 2 basic types of tasks. Either your routine detects events or helps to detect events, or your routine responds to an event and provides some kind of a service. So an event detector could be something like, is sunny outside now, as opposed to 5 minutes ago. Service could be extend patio shade. So if you had an automated patio shade that detected when the sun is now outside versus when it wasn't, then it can have a service that extends the patio shade automatically. Rule number 2 is to keep your event detector and service routines as short and as fast as possible. That means decompose. Decompose your problem into as many small and tiny little bits as you can. Rule number 3, no blocking code allowed. This means no waiting, no delay. If you use blocking code, it breaks rule number 2, because there's an undetermined time, or sometimes a determined but very long time, spent waiting. If you say, wait while button not pressed, this is bad. If you need to delay something, I will move this up here. I'll write this up here. If you need to delay something, use a timer and check for timer expiration. I won't go into detail what that means now, but you'll certainly learn about it later. So what does ENS actually look like? Your whole program is broken down into this structure here. Step 1, initialize all your hardware and software. So turn on the various inputs and outputs that you need. Initialize the chips, initialize your A to D converter, your D to A converter. And then you go into a loop where you test for events. You perform some sort of service when event is detected. And you repeat that loop until you run out of power. When you test for events, there's 2 different ways of doing things. You can round robin them, so test all of them every time. Or you can do priority scanning, which means some events are higher priority than other events which are lower priority. So for instance, user interaction might be rated as higher priority, whereas obstacle avoidance may be lower priority. The simplest incarnation is, again, think of this remote control, right? Where you have one state and many loopback transitions with associated events and actions. In this structure would look like a single loop with X number of possible events and Y number of possible actions or services. And that would be it. The one loop would just keep running, keep running, keep running. When you transition states, the way this frequently looks in software is either your loop does something different, or you transition to different loop. So that's the more advanced multiple state incarnation. Right now we're just looking at this at the basic. For lab 2, we have a device called the cockroach. This particular slide is based on an old incarnation of the cockroach, which is, as of this recording, perhaps about 15 years old now, but is subject to change in the future. I don't know how long this lecture will be used for. The goal of Lab 2 is to program this ME210 cockroach to mimic the behavior of a real cockroach. When exposed to light, it scurries around and looks for the darkness. When darkness is found, it stops scurrying around. If it contacts objects, it evades them and tries to turn around and go the other way. And it doesn't have to live for weeks after decapitation, but if it does, you get bonus points. There are 4 types of input on the particular incarnation of the cockroach we currently have, which is there are light sensors. There are 3 photocells on top that can detect the visible spectrum of light. There are bumpers. So if you think of the cockroach as sort of oblong shape here, there's a front left bumper, a front right bumper, a back left bumper, and a back right bumper. Timers are in software and implemented in hardware on the Arduino. And keyboard. The keyboard's not based on an actual cockroach sense, but it's just for debugging. And as far as output goes, the Roach has 2 different possible outputs. You have motors, 2 motors, a right and a left. And you have monitor. You have a way to get text output to the computer. Again, not based on a real cockroach ability, also for debugging purposes. So really, the motor is the only real output here. So your cockroach has these input states, these input types, which can generate events. What the events actually are is up to you to decide. And then the actions, the possible actions, are just things having to do with the 2 motors on the cockroach. If we take a crude start at decomposing the cockroach behavior into events and services, what kinds of events might we be looking for? You can pause the video now and try and list out a bunch of events and services that you might think you'd need to implement your cockroach. Here's some examples of events that we might use. Light goes from dark to bright. That would imply that either somebody has turned on a light or we've moved into a light area. You could have the opposite. If the light goes from bright to dark, that might mean that somebody has turned off a light or that we've moved into a darker area. Any one of the 4 bumpers, or perhaps a combination of them, could be hit. Or you could use a timer, right? Timer expires. Some examples of services: motors or motors could go on or off, or maybe half speed. You could do turning by turning tank style, where you have left go forward and the right motor go reverse. You could also print to screen if you're debugging. That's a service. So then, based on whatever your state diagram is for your implementation of cockroach behavior, some events may result in some services and some might not. In practice, we have a Roach library called RoachLib that abstracts some of the programming nitty-gritty for you. You would initialize all of the robot hardware. If we go back to the slide about this step 1 here, initialize hardware and software, that's this function here. This is step 1. Initialize all of the software and hardware for the Roach. Do we have functions available for controlling the motors? One that does left motor speed, one that does right motor speed, where X is a 8-byte signed variable that you can assign from -10 to 10 based on whether you want it to go full speed forward or full speed reverse or something in between. So this is an example of a service for the cockroach, right? Motor speed is not an event, it's a service. We have a function for checking the bumpers. So read bumpers returns an 8-bit value, or 1 byte, excuse me, that represents state of all bumpers. I will write this better. for bumper switches. And lastly, we have a function for reading the light level. Notice how read bumpers and light level don't actually tell you that an event has happened or not. So you would have to write a function that wraps around them that says maybe bumpers hit or light gone dark. That would read the bumper state or read the light level, compare it to something from the past maybe, and then decide, has there been an event? There's a library that helps you with timers. The timer library, which you will also be using later on for the project, it's not Roach specific, has 16 timers. You initialize the timer by calling this function timer ARD init timer, where the time interval variable is your tick count and number is the timer number. So I could go, I want to initialize time number 0 to 1,000 ticks, and that would be 1,000 milliseconds, so it would be a 1-second timer. After you've set the timer, you then check if it's expired by calling this function here. This is an event checker. It will tell you if the timer is transitioned from being running to expired or stopped. You can then clear the expired flag by calling this function here with the same timer number that you were using, that you were checking earlier. Lots of other stuff in this library as well, including something that's like get time. Please do not use get time, right? We see a lot of this while get time is less than equal to some number x. Don't do that. That's blocking code, all right? What we want is, we want to see people use the timers in a way that is compatible with an events and services framework that is using this is timer expired to do proper event checking on the timers. Lastly, one of the things that you'll be asked to do in Lab 2 also is to write pseudocode. So I'll give you a brief overview of what pseudocode means. Like state diagrams, pseudocode's a way to decompose a problem and plan a solution conceptually before you even ever sit down at a computer to start writing code. So it's a written low-level exploration of how to implement an algorithm. It's written in English or your favorite non-machine language. I haven't seen Klingon yet, but the first person to do so gets some bonus points as well. And it doesn't use the syntax of any specific programming language. So it's syntax that is grammatically consistent, but it does not require programming knowledge to actually understand. What might it look like? This is decent pseudocode. If light is on, drive forward. If object has been hit, turn, reverse the motor, turn right, set timer. End if. So these statements bracket the various if statements. If timer is expired, then straighten the steering wheels, drive forward. It is, you can almost read this and figure out what it's doing without knowing anything about programming. What we see sometimes are things that look like this. This is not pseudocode. It looks almost like code. It requires programming knowledge to know what these brackets do, what this means. But it's still unintelligible. It doesn't actually help me or the TAs or anybody you're trying to actually get help from with your program. It doesn't help them understand what it's supposed to be doing or what you intend for it to be doing. So don't do this. It doesn't help you structure your program any more than writing straight C would. In fact, writing straight C would be better than trying to write this sort of heavily syntactic intermediary. So this is the end of the event-driven programming lecture. I hope that it was informative. And in the next lecture, we'll get into some of the nuts and bolts of programming, including data types and operators and that sort of thing. But until then, you have enough knowledge to start on the Lab 2 pre-lab. Thank you.